How our planet came to be. The Earth, our home planet, is unlike any other planet in the universe. What makes it completely unique is its ability to support life. This innate setting results from a nebulous collection of floating gas and dust. As a matter of fact, the Earth has evolved into a planet filled with rocky terrains, a life-supporting environment, and mysterious oceans. The bizarre disruption by a supernova explosion, as well as the ferocity of cosmic missile strikes, brought about the universe. Face-killer dinosaurs, saber-toothed tigers, mammoths, and an unending list of extinct creatures have all crept the surface of the Earth. But to make sense of Earth's primordial backstory, we need to take a few steps back into history. From the Earth, if you look out into space, you will see a vast cosmos filled with billions of stars and galaxies. As a matter of fact, our universe wasn't always like that. Billions of years ago, the universe would probably fit into the palm of your hand because it was so little. The galaxies, the stars, and all the elements that make up life were formed from this little universe. Existing only as a massive cloud of dust and gas, the Earth and the rest of our solar system were completely unrecognizable billions of years ago. That dusty cloud eventually experienced a disturbance due to a mysterious event that even the top scientists in the world are still unable to explain. This disturbance triggered a series of subsequent events that eventually resulted in the emergence of life as we know it. One widely held theory among scientists is that the dust cloud came together due to disruption produced by a supernova explosion that resulted from the collapse of a far-off star. This resulted in the formation of a solar nebula, a rotating disk of gas and dust. The dust and gas were more tightly packed at the core of the cloud as it spun faster, which in one way increased the nebula's speed. Hydrogen atoms started to move more quickly and furiously as the gravity at the cloud's core increased over time. The protons in the hydrogen started fusing, creating helium and unleashing a tremendous quantity of energy. This resulted in the birth of the Sun and the star that serves as the focal point of our universe. However, it would take longer for the planets to form. The leftover matter began to clump up as the Sun started to develop. Planetesimals were created by the accretion of small grains within the disk. A clump's gravitational attraction increased with size, which in turn accelerated growth. Smaller particles gravitationally attracted and joined to form larger particles. Lighter elements like hydrogen and helium were carried away by the solar wind, a continuous stream of charged particles that emanates from the sun's upper atmosphere. Smaller terrestrial worlds like Earth were created from the hefty, rocky components that were left behind. The solar wind also has less of an impact on lighter components as they traveled farther from the sun, allowing these elements to combine into gas giants. The planets, moons, asteroids, and comets in our solar system were produced by this process. The first planet to fully consolidate and clear its orbit around a core of heavy metal and rock would have been an early version of Jupiter. Jupiter's predominantly hydrogen-based atmosphere was crushed by its powerful attraction. Jupiter's gas has been found to be orbiting nearby stars as a result of our observations of exoplanets. According to astronomers, the young Jupiter would have started moving in the direction of the Sun, bringing comets and asteroids with it. But as Jupiter was forced into an orbital resonance with the approaching Saturn, its inward trajectory was reversed. Not every planet that formed in the early solar system continued to revolve around the Sun. The larger gravitational field would deflect smaller objects traversing a planet, or possibly grab them and turn them into moons. The 4 remaining terrestrial planets are believed to have developed from up to 20 smaller planets that once orbited the inner solar system. As the planetary system was still forming, collisions were frequent, and the Apollo moon rocks provide evidence that an early Earth-Moon collision played a significant role in the formation of our planet. First, the rocky core of Earth developed as a result of collisions and binding of heavy elements. Lighter material formed the protoplanet's crust, while denser stuff settled to its center. Around this time, scientists believed that Earth's magnetic field probably began to form. Early in the course of Earth's history, a massive body collided with the planet, releasing fragments of the newborn planet's mantle into space. The moon was created when gravity brought many of these pieces together. The moon then entered an orbit around its origin. Gravitational study indicates that the moon's core is lighter than anticipated and that the Earth's iron core is greater than originally expected. The loss of a large portion of the moon's heavy material to the larger Earth may be accounted for by a collision between the two bodies. A glancing blow from the impact sent the Earth spinning quickly with a 5-hour day. The molten debris eventually became the moon that we see today. Despite not being the largest moon in the solar system, our moon is the closest in mass to its parent planet. Over extended periods, the moon has a considerable stabilizing impact on the Earth's rotation. Without the moon's help, this variance may reach 85 degrees, which would have grave consequences for the stability of the climate. The planets in the early solar system removed the debris during a time of intense bombardment. The newly formed Earth was dotted with asteroids and comets that brought water, essential for life, while tectonic forces removed the scars left by the bombardment. The moon, which went through the same struggles, still has craters on it. The newborn Earth was in a special location when the turbulence in the forming solar system calmed down. Even though there aren't many comets and asteroids moving through the inner solar system right now, there were many more of them when the planets and sun were still young. Most of the water on Earth's surface was likely deposited by collisions between these cosmic entities. The abundance of water on the planet needed to exist in liquid form. Therefore, the Earth's distance from the Sun was exactly ideal. Our planet is located in the so-called Goldilocks zone, an area close enough to a star for liquid water to exist on a planet's surface without freezing or evaporating. Many experts believe that the presence of liquid water and being in this zone are crucial factors in the occurrence of life. The movement of the massive rock plates on the surface of the universe is a result of plate tectonics, which is caused by the mantle's flow beneath the crust of the planet. Mountains and volcanoes were created as a result of collisions and friction, which also caused gas emissions. Almost no atmosphere was present when Earth initially formed. As the planet began to cool and gravity gathered gases from Earth's volcanoes, its atmosphere started to form. According to the geological record, oxygen first appeared in the atmosphere about 2.7 billion years ago. As iron in the oceans combined with newly abundant oxygen to make iron oxide, the vast iron ore districts of Western Australia were created. Simple plant life relied on carbon dioxide and sunlight to survive, and as waste, it produced extremely reactive oxygen. This made it possible for more sophisticated life to develop, creating a complex network of interconnected plants and animals that completely changed the world. Other severe effects of atmospheric change were experienced. The air's high levels of insulating gases were largely removed by oxygen, which significantly cooled the Earth. At this time, a series of ice ages started. However, there is a ton of evidence that the world has experienced ice interspersed with warm periods. These cycles are brought on by complicated circumstances. Fault lines are indicators of how continents have moved, which has caused divergence in ocean currents. A planet's eccentric orbit around the Sun and variations in the Earth's axis direction is a result of volcanic activity in the atmosphere. Each of them contributes to long-term changes in the planet's climate. An accurate technique to determine how the composition of the atmosphere has evolved over the last 800,000 years is to analyze ice cores that were accumulated in the Antarctic or Greenland. It is possible to precisely sample air bubbles that are captured between snowflakes before becoming rigidly imprisoned as the snow turns into ice. In the long run, galaxies will split away when our sun has ceased to exist 100 billion years from now. The cosmos will consist of solitary stars that are exhausting their vitality, while others will disintegrate into neutron stars or black holes. Some may turn into white or brown dwarfs. After the Big Bang, millions of trillions of years from now, even black holes will disappear. All matter eventually breaks down into its constituent parts. Even protons, which serve as the foundation of an atom, can decay. Most likely, the most gloomy future is one in which the universe turns cold, black, and empty. Space will eventually become dead and empty as the universe continues to expand and galaxies move farther apart from one another. Our galaxy will leave the nighttime sky because it will be traveling farther from us than the speed of light. Everything will eventually just sort of decompress, and that will be the end of it. The cosmos will eventually perish, leaving nothing but a chilly, dark, and dead emptiness.